Hi, I'm Yash Mehta from Mooresville, North Carolina. I'm in the ninth grade at Durham Academy High School, and I want to share a project that is really close to my heart. My grandfather was a strong supporter of a small school for the blind in Old Delhi, India. During our visits, I noticed that the students weren't using electronic braille displays, which I expected. When I asked why, I learned it was due to cost. This revelation inspired me to reduce the cost of braille displays for the visually impaired by utilizing brushed, coreless motors instead of expensive piezoelectric actuators. This is crucial because there are currently 36 million visually impaired individuals around the world, and this number is projected to increase by 55% over the next 30 years. Additionally, 89% of blind individuals live in low and medium income countries where access to Braille is very limited. Braille enables visually impaired individuals to read and learn. Braille cells consist of 6 dots arranged in 2 columns and 3 rows, and they can be read either on embossed paper or using Braille displays. Braille displays are expensive because they rely on piezoelectric crystals, which require complex hardware, driving up costs and leading to mechanical failures, such as sticking dots. Printed Braille is also costly. It is up to 6 times more than regular books due to the specialized manufacturing process. Additionally, for visually impaired individuals with sensitivity issues, current Braille technologies are even less accessible, as they can't effectively feel the rigid static dots of Braille. Reducing the cost of Braille displays is critical to making education more accessible for everyone, and finding a new way of conveying Braille is especially important to those with sensitivity challenges.
My project uses readily available parts like motor drivers and inexpensive brush motors to optimize the braille cell cost. The single cell model costs only $20 to make, and the 4 cell model is predicted to be $35. I filed a provisional patent to protect this technology. I also added a potentiometer to let users adjust the speed of the braille cell output. This device is life-changing for blind individuals with finger sensitivity issues, as the rotating and vibrating effects of the motors make braille learning accessible, allowing users to adjust intensity and educate themselves comfortably. The development process included several iterations, starting with a TENS unit that applies electric current through a cathode and anode to a custom braille cell with wires.
I gathered data from visually impaired individuals at the Blind Relief Association in New Delhi, India. The Braille cell with motors spaced 6 millimeters apart yielded the highest accuracy. This supports my hypothesis that increasing the distance between motors improves accuracy, as the human finger struggles to distinguish closely spaced stimuli. I tested this by modifying the distance between the Braille dots using a custom 3D printed mount and calipers. My research on the 2-point discrimination test showed that the average finger can accurately detect dots spaced 6 millimeters apart, which was directly relevant to my project. In the future, I plan to integrate an ESP32, an inexpensive microcontroller that offers enhanced functionality, including Wi-Fi, Bluetooth, and OCR using Python libraries. This will allow users to take pictures of printed text via their phone and convert it into Braille, or send text through a custom web page directly to the Braille display. I will also gather additional feedback from visually impaired individuals to enhance user friendliness. And finally, I will partner with an ethical corporation to refine the design for production, keep the price below $50, and provide at least 1,000 free units per year to underprivileged blind individuals in developing nations. Thank you for listening.